Hello, everybody. Welcome to our big data final project here at the end of the semester. And we do have two of my friend here, Juncheng and Jose here. We're gonna work all together for this final project. So pretty much what I did here is me and Juncheng we did part one on process three different data sets using DNN, CNN, long short time memory, and also the GRU to process to machine learns all the three different data set, and then Jose is in charge of the second part. But yeah, let's dive in right away because we have a lot of slides here, and I don't think we have enough time here. So of course, the first thing, let me just introduce yourself, you guys, kind of what we did here. Some of the conclusions, some of the introduction. DN model is as we all learn the past 2 months, and we should be pretty familiar with what are these are. Same as seeing in long short time memory and also the GRU method. It's one of the RNN machine learning method here. And also one of the needs that was introduced, which is a CLR, which are the correct learning reproducibility. So that at this time, we are running every data set at least 5 different times, and every time we're using 100 epochs here. What's the point of that is we're trying to find the correct learning reproducibility, and we're trying to say, hey, which machine learning, what layer we use to create a better result here, and that's why we have the CLR here. And then the second thing is the D index, as we learned last semester. The D index is a value from 0 to 2, and when it's closer to 2, that means it does a really good job. And whenever it's lower than 1, it's kind of tell you, hey, this model here didn't do a good job. Now, of course, one of the things that we mentioned is the seeding method. Seeding method is everybody know, deep learning method, they always struggle with reproducibility. And this is why we're using seeding here. Seeding creates, it helps with all these data set, helps with our machine learning method with their better reproducibility. And then let's jump right into the first data set we have here, the MNIST data, a well-known data set that, it contains about 70,000 image data, and then every of them are 28 times 28 pixels. And then we're going to jump right in here as we data pre-process is definitely one of the most important thing as a data scientist. See what we did here. We kind of normalize the data, divide by 255, and now we're going to reshape the data as one thing that we learned, one hot encoder, one hot encoding, and of course, the last line here, we're going to split the data into train and test here. And this is our first DNN model right here. It did a really good job, as we can see on the right. The accuracy is all pretty high on the right. These are all 5 different runs. The index stores are closer to 2. So that tells a good job. And the CLR right here, which are the average the 5 different accuracies we have is 0.97. It did a really good job. And these are the D index here, as they're all closer to 2.0. And also on the left, we have the model layers displayed on the left. And then the second layer, CNN model, similar thing. They did a pretty good job, have an average of 0.98 on the accuracy. Really good data set, really well-known and well-structured. Same as long short time memory here, pretty high score. GRU, the model on the right, the structure on the right, and then we have 0.98 success rate. And then what we're going to do is we're going to use the PCA and TSNE. We're going to pre-process this data and then see what we have here. Look at the code we have. We have the PCA right here. We choose 50 as the end component. And of course, TSNE, here are some of the parameter that we set here. And all those are the 4 different results. And I didn't go through put all 5 different run graphic on here because that just takes a long time and it kind of doesn't mean anything. So I just picked some of the good results here. And we all know the MNIST data, it's well structured. So all these results runs pretty good. And 7 layers, these are the models that we choose for the 7-layer PCA and TSNE pre-process here. And the last step, the last question that I asked is only do PCA instead of PCA and TSNE. So here's what we did. Of course, we don't have TSNE over here. And then those are some of the results. And we can see the last one, which is the GRU. It kind of have a little thing going on here. But as we all know, it's well-structured data set. It has a pretty high score, nearly to 1.0. And the reason is why also we have this conclusion here. All the machine learning method did really good job on all different pre-processing. Either you choose to use PCA TSNE or if you choose not to use TSNE. And that's just because the MNIST data, it's a consistent, clean, and normalized image data. So that's what we have here for the MNIST data. And also the second data set we have is the EMODB data set. Here's a screenshot I have. As we can see on the right, which is we have the file label here. It's a label from with 7 different emotional tones here, which are represented from 0 to 6. As we keep going on pre-processing here, and then this data, I did not get a chance to take a screenshot of the left column, but on the first column, it's a I believe it's a name column, which doesn't mean anything, so I just dropped it right here. And then we have our DNN model. As we can see here, this data set is not as well structured as the MNIST data. Of course, as we can see, our accuracy are 0.8. Over here, they're all pretty good with a D index of 1.7, which is definitely an acceptable success rate that we have over here. Some of the D index visualization we have here, and also on the left, we have the model structure. CN model right here, it didn't do as good as the DN 0.67, which is all right. As we can see on the right, the D index score it's above 1.5, which is pretty good. And long short time memory model we have here, which we have a success rate accuracy of 0.61, and the GRU slightly higher, 0.63 here. And then what we're going to do, of course, PCA and TSNE, we're going to use these pre-processing. We're going to see, hey, what are the results that we have here? As we can see, hey, they did a pretty good job on our train and loss function in all the graphic what we have here. Same as TSNE, same as the 7-layer. These are the layers that we choose. They all did a pretty good job on here, and those are some of the DN model seeing in long short time memory and also GRU right over here. And the last one is the PCA pre-processing we have. And as we can see, we have higher scores comparing to before we're doing the PCA. As we looking at those data set, they did a pretty good job over here. And then some of the conclusion, the reason why PCA produce more consistent and global information, but whenever you use TSNE, it didn't do a very good job because the TSNE is suited to looking at the whole picture of the data set. It says here visualization rather than the feature engineering as we are doing here are trying to predict the label from 0 to 6 here. And then the third data set, Edison, you did this part, and you are definitely one of the best data scientists that I ever met. So tell us more. Tell us something about this data set. What's so cool about it, and what are some of the difficulties that you run into whenever you're handling this data set?
Yeah, I'll just start sharing my screen.
Oh yes.
Yep. You have to give me the permission.
Yes. I should be able to share right now.
Is it working?
Yes.
Let me get to the slides. Okay, so we have the KOLD data set, which is like a single cell RNA sequencing data. It has 700 samples across 3 classes, and each class is like a cell type. And the data set is very high dimensional because it has like 10,000 features and only 700 samples. And here's the results for the deep neural network for 5 rounds. And for each of them, we have like perfect results, which might be like overfitting. Because we only have, I'm guessing the reason is that we only have like 700 observations. And from my experience, I think this data set it's just a subset of like a bigger data set. Because I did research on this with Dr. Han, and the original data set has like 14 cell types, and the file is about a couple of gigs. So I think it's just a subset of data set. We need more data to like prevent the overfeeding. And here's the CLR, and it's a perfect result. Here's the CNN model. Again, it's like overfitted. Here's the CLR for the CNN. It's 0.99. And here's the LSTM. And LSTM didn't do really well before dimensionality reduction. And here's the CLR for the GRU. It's the same thing. I'm guessing is that RN is not really good for this data set before like we do dimensional reduction. And here we did PCE plus t-SNE on the single cell RNA sequencing data. And here's the results for everything is just like 99% after we did dimensional nodality reduction. And here we did the 7 layers. And the results, it's perfect. And lastly, we did PCA pre-processing. Here's the results. It's a very similar results. And CRR for PCA for all the models is 98%, 99%. And the data set is a high dimensional sparse matrix, which means that many of the cells in the data sets is 0, which is challenging to process. And before doing any dimensional reduction, most model perform poorly, especially the LSTM and GRU. And after performing t-SNE and PCA, the performance increased dramatically.
Sounds good. Sounds good, Jincheng. I just have one question. See, you worked the whole data set, so and also you mentioned earlier, with only 700 features, well, 700 samples, it didn't do a good job. It looks like we're having some overfitting issue. And of course, the label is only from 0 to 2, 0, 1, 2, these 3 different labels. Whenever
Yeah.
you're working with the whole data set, you have how many samples do you have?
I have around like 10,000.
10,000 different samples. And also you said you have different label from 0 to about 40.
14 cell types.
14
Yeah.
labels. And you said the more sample that you have, it kind of helps with overfitting. And do you think when there are more labels, it helps with overfitting? What do you think?
More labels just making it like more difficult to like classify.
more difficult to classify. And
Yeah.
also, I think that's
Yeah,
why whenever
like deep learning models often works with like a lot of data. Yeah, it
right.
requires a lot of data to learn.
Sounds good. Sounds good. Thank you. Thank you, Junsheng. You
Yep.
did a really good job on that third part. But now we're gonna move on to the part two of our project here. And Jose did an amazing job here. Why don't you take over, Jose, and tell us what you did here.
So share my screen.
Okay, sounds good. Yeah, just let me share really quick. Mm. Are you able to see it now or?
Yes.
Okay. Yeah, so part two kind of was over looking at the credit risk data and essentially trying to find out, I guess, how you would evaluate someone. I guess you could be used if you want. I guess they can be used in different ways, but this one, I guess, they want to label them if there would be delinquency or non-delinquency. So I guess depending on the context, it could be maybe to approve them or not to approve them, or to say they have a good or bad credit. But essentially we used three models for this one. It was CNN, LSTM, and GRU. And it was essentially to go just to class. It was a classification data, so for either delinquency or non-delinquency. And then one of the things I like to do usually just run like a feature importance score just to see right off the bat maybe roughly what kind of has a little bit more importance towards the model. So in this case, it was the revolving credit percentage, which I think is kind of just simply like your ratio, how much credit you use versus like debt. So it's just some calculation along those lines. And then just a quick like preview of how the data was. Uh, they just had a few different things from like obviously what we're trying to predict within the delinquency to the one I just mentioned, and like various types of like past due payments from that would range from like 60 days, 90 days, and their income, things like that. And then one of the first things that we were doing was just a visualization. So we did like really three visualizations types. One of them was the FAD, which is kind of tries to do like almost kind of like a heat type of matrix you've calculated through like diffusions. But it essentially kind of just looking at this one, we couldn't really find any real like major distinctions with our classifications. Maybe it kind of shows that inside there's smaller clusters that could help us with that, but nothing from like the outside. The same thing with like the TSNE. In some areas, it showed one a little bit stronger, but for the most part, it was definitely overwhelmed in one direction. And then with the PCA, even though it kind of showed like it could maybe have a better split than the other ones. But that one was really just added mainly because we were instructed to kind of combine PCA with TSNE, which is kind of what we'll see here, which overall did a little bit better than just the TSNE, but kind of just looking at all these visualizations, we couldn't really find any like initial like major distinct patterns that could kind of maybe give us some type of insight early on. And yeah, that's just kind of summarize everything I just said. And then right now, I'll just go over some of how we trained the models. So at least for me, it was taking roughly anywhere from like 1 to like 3 hours just to train a model. And roughly I had to run about 9. So I kept it just to 4 layers. And for the most part, they were done really the same way. So this was for the CNN uh LSTM model, the GRU. And then so for the first results within the CNN, the accuracy was actually really good. You see it had a 93%. But I guess kind of part of the reason why it ended up being like this was I guess kind of how we saw the structure of the data. Uh, Overwhelmingly it showed it going one way over the other, which essentially if it just guesses that only, it's gonna have a higher accuracy than not. Because we can see right here within like the recall, for example, it did really poorly. And the recall is kind of essentially just kind of like the ratio like your correct guesses over the entire I guess like so I guess your correct positive guesses over the entire positive population, which includes the correct ones I just mentioned, but also like the false negatives. And then we'll see that that trend will continue within the other ones. But this was just essentially just the validation and the validation accuracy. How essentially it was doing a little bit better, but as we can see, kind of like the difference between the bottom end and the top end is really not that major of a factor. It was pretty minuscule, but the last one is kind of what shows that it kind of like didn't do as good as I guess you would think if you just base it off solely on accuracy. And then this was kind of the results from the LSTM. Again, it was pretty similar, pretty high accuracy score. Again, the recall is pretty low, precision is pretty low. And again, pretty much the same results. Increasing the epochs didn't like do too much. Everything stayed really close because the difference from like 0.34 and all the way up to like 939 is like 0.005. So kind of going through more and more data didn't really help either. And then for our GRU, this one I guess did a little bit better, but even then it's still kind of along the lower side within the recall and the F1 score. So all of these kind of did really bad predicting the one classifications. And then here's the maps again. And then this is just kind of a summary of everything I said. Everything kind of really had a higher accuracy score, about 93%. But everything within the recall was under like 0.2 really. Besides GRU, they had a 0.21. And then, so in order to see if we can maybe potentially improve this, we did 2 resampling methods. It was Smote and Edison. And essentially this is just kind of how we resampled the data from that. And then essentially from here, this is kind of where we ran the same 3 models again, but based off each resampling. So it was 6 total models. So just to keep everything like shorter, especially since these kind of started running a lot longer than the initial 3, kept it to 4 layers. And then they were all really just constructed the same way. And then so for our initial one, with CNN and SMOT, it was it did a little bit better, especially within the recall, but even then it kind of really wasn't as good as we have liked. The accuracy did go down in this case, but I guess it does help with like not just like I guess it gives more balance like approach and kind of a little bit more, even though the accuracy is less, I think it kind of gives a better like accuracy overall in terms of like using this in like a real world setting. And then with the other sampling method, again, pretty similar to the one before. I would say this one kind of did perform a little bit worse, but the accuracy went down as well. And then with the LSTM model, again, the scores were all kind of really similar, as we'll kind of see. And then this one was the worst one out of the both LSTMs. And then again, if you will kind of see with even with the GRU, the next one will be the best one, but even then, the recall never really got like super high either. But I think I would say kind of the biggest thing that you can get from this is that obviously when you have a really big class imbalance, obviously you can get like a really high accuracy score if you just predict the one that has within like the majority class, for example, but that doesn't really do a good job of maybe painting an accurate picture, especially if maybe you want to actually use this in a real world setting, because in that case, you'll never get the minority class, you'll never identify those. And sometimes that could be like maybe looking for cancer in somebody. And if you get all those instances wrong, you're not really doing anyone a favors. And yeah, that was really it though.
Sounds good. Sounds good, Jose. Yeah, it was really good job. And you mentioned whenever you training the data set, it took a long time. How long did it take for you run this whole part 2 of the project?
I think if I had to add everything up, it was roughly probably about like 14 hours.
14 hours. Totally, yeah. Whenever me and Juncheng was working on the first part, the MNIST data is taking the longest time. It took about 20 hours to run the whole thing, especially we're doing 100 epochs every run, and then we're doing 5 runs for one machine learning method, machine model here. And then that just took us a long time to compare our the CLR that we have here. But definitely, I'm so grateful that I have the chance to, to get hands on these real world data sets, and we can see, hey, what feels like dealing with the imbalanced data as Jose did here, and also what we can see as well whenever we're dealing with Juncheng's data set, the RNA sequence data set, they're super high dimensional, and what should we do to avoid overfitting, and also the MNIST data set as well known as their well structured data set. And thank you so much everybody for watching, and this is the end of our project. Thank you.
Thank you.
Thank you.